1910.1028 Appendix D. Sampling and Analytical Methods for Benzene Monitoring and Measurement Procedures. Appendix D to Section 1910.1028 Sampling and Analytical Methods for Benzene Monitoring and Measurement Procedures. Measurements taken for the purpose of determining employee exposure to benzene are best taken so that the representative average 8-hour exposure may be determined from a single 8-hour sample or two 4-hour samples. Short-time interval samples, or grab samples, may also be used to determine average exposure level if a minimum of 5 measurements are taken in a random manner over the 8-hour work shift. Random sampling means that any portion of the work shift has the same change of being sampled as any other. The arithmetic average of all such random samples taken on one work shift is an estimate of an employee's average level of exposure for that work shift. Air samples should be taken in the employee's breathing zone, air that would most nearly represent that inhaled by the employee. Sampling and analysis must be performed with procedures meeting the requirements of the standard. There are a number of methods available for monitoring employee exposures to benzene. The sampling and analysis may be performed by collection of the benzene vapor or charcoal absorption tubes, with subsequent chemical analysis by gas chromatography. Sampling and analysis may also be performed by portable direct reading instruments, real-time continuous monitoring systems, passive dosimeters, or other suitable methods. The employer has the obligation of selecting a monitoring method which meets the accuracy and precision requirements of the standard under his unique field conditions. The standard requires that the method of monitoring must have an accuracy, to a 95% confidence level, of not less than plus or minus 25% for concentrations of benzene greater than or equal to 0.5 ppm. The OSHA laboratory modified NIOSH method S311 and evaluated it at a benzene air concentration of 1 ppm. A procedure for determining the benzene concentration in bulk material samples was also evaluated. This work, reported in OSHA Laboratory Method No. 12, includes the following 2 analytical procedures. I. OSHA Method 12 for air samples. Analyte, benzene. Matrix, air. Procedure, adsorption on charcoal, desorption with carbon disulfide, analysis by GC. Detection limit, 0.04 ppm. Recommended air volume and sampling rate, 10 L to 0.2 liters per minute. 1. Principle of the method. 1.1. A known volume of air is drawn through a charcoal tube to trap the organic vapors present. 1.2. The charcoal in the tube is transferred to a small, stoppered vial, and the analyte is desorbed with carbon disulfide. 1.3. An aliquot of the desorbed sample is injected into a gas chromatograph. 1.4. The area of the resulting peak is determined and compared with areas obtained from standards. 2. Advantages and disadvantages of the method. 2.1. The sampling device is small, portable, and involved no liquids. Interferences are minimal, and most of those which do occur can be eliminated by altering chromatographic conditions. The samples are analyzed by means of a quick, instrumental method. 2.2. The amount of sample which can be taken is limited by the number of milligrams that the tube will hold before overloading. When the sample value obtained for the backup section of the charcoal tube exceeds 25% of that found on the front section, the possibility of sample loss exists. 3. Apparatus. 3.1. A calibrated personal sampling pump whose flow can be determined within plus or minus 5% at the recommended flow rate. 3.2. Charcoal tubes, glass with both ends flame sealed, 7 cm long with a 6 mm OD and a 4 mm ID, containing 2 sections of 20/40 mesh activated charcoal separated by a 2 mm portion of urethane foam. The activated charcoal is prepared from coconut shells and is fired at 600 degrees Celsius prior to packing. The adsorbing section contains 100 mg of charcoal, the backup section 50 mg. A 3 mm portion of urethane foam is placed between the outlet end of the tube and the backup section. A plug of silanized glass wool is placed in front of the adsorbing section. The pressure drop across the tube must be less than 1 inch of mercury at a flow rate of 1 liter per minute. 3.3. Gas chromatograph equipped with a flame ionization detector. 3.4. Column, 10 feet x 1/8 inch stainless steel, packed with 80/100 Supalcoport coated with 20% SP2100, 0.1% CW1500. 3.5. An electronic integrator or some other suitable method for measuring peak area. 3.6. 2 ml sample vials with Teflon-lined caps. 3.7. Microliter syringes, 10 microliter, 10L syringe, and other convenient sizes for making standards, 1L syringe for sample injections. 3.8. Pipettes, 1 ml delivery pipettes. 3.9. Volumetric flasks, convenient sizes for making standard solutions. 4. Reagents. 4.1. Chromatographic quality carbon disulfide, CS2. Most commercially available carbon disulfide contains a trace of benzene which must be removed. It can be removed with the following procedure. Heat under reflux for 2 to 3 hours, 500 ml of carbon disulfide, 10 ml concentrated sulfuric acid, and 5 drops of concentrated nitric acid. The benzene is converted to nitrobenzene. The carbon disulfide layer is removed, dried with anhydrous sodium sulfate, and distilled. The recovered carbon disulfide should be benzene-free. It has recently been determined that benzene can also be removed by passing the carbon disulfide through 13x molecular sieve. 4.2. Benzene, reagent grade. 4.3. P-cymene, reagent grade, internal standard. 4.4. Desorbing reagent. The desorbing reagent is prepared by adding 0.05 ml of P-cymene per milliliter of carbon disulfide. The internal standard offers a convenient means correcting analytical response for slight inconsistencies in the size of sample injections. If the external standard technique is preferred, the internal standard can be eliminated. 4.5. Purified GC-grade helium, hydrogen, and air. 5. Procedure. 5.1. Cleaning of equipment. All glassware used for the laboratory analysis should be properly cleaned and free of organics which could interfere in the analysis. 5.2. Calibration of personal pumps. Each pump must be calibrated with a representative charcoal tube in the line. 5.3. Collection and shipping of samples. 5.3.1. Immediately before sampling, break the ends of the tube to provide an opening at least 1/2 the internal diameter of the tube, 2 mm. 5.3.2. The smaller section of the charcoal is used as the backup and should be placed nearest the sampling pump. 5.3.3. The charcoal tube should be placed in a vertical position during sampling to minimize channeling through the charcoal. 5.3.4. Air being sampled should not be passed through any hose or tubing before entering the charcoal tube. 5.3.5. A sample size of 10 liters is recommended. Sample at a flow rate of approximately 0.2 liters per minute. The flow rate should be known with an accuracy of at least plus or minus 5%. 5.3.6. The charcoal tubes should be capped with the supplied plastic caps immediately after sampling. 5.3.7. Submit at least one blank tube, a charcoal tube subjected to the same handling procedures, without having any air drawn through it, with each set of samples. 5.3.8. Take necessary shipping and packing precautions to minimize breakage of samples. 5.4. Analysis of samples. 5.4.1. Preparation of samples. In preparation for analysis, each charcoal tube is scored with a file in front of the first section of charcoal and broken open. The glass wool is removed and discarded. The charcoal in the first, larger, section is transferred to a 2 ml vial. The separating section of foam is removed and discarded. The second section is transferred to another capped vial. These two sections are analyzed separately. 5.4.2. Desorption of samples. Prior to analysis, 1 ml of desorbing solution is pipetted into each sample container. The desorbing solution consists of 0.05 L internal standard per ml of carbon disulfide. The sample vials are capped as soon as the solvent is added. Desorption should be done for 30 minutes with occasional shaking. 5.4.3. GC conditions. Typical operating conditions for the gas chromatograph are 1.30 ml per minute, 60 sig, helium carrier gas flow. 2.30 milliliters per minute, 40 sig, hydrogen gas flow to detector. 3.240 milliliters per minute, 40 sig, airflow to detector. 4.150 degrees Celsius injector temperature. 5.250 degrees Celsius detector temperature. 6.100 degrees Celsius column temperature. 5.4.4 Injection size 1L. 5.4.5 Measurement of area. The peak areas are measured by an electronic integrator or some other suitable form of area measurement. 5.4.6 An internal standard procedure is used. The integrator is calibrated to report results in ppm for a 10-liter air sample after correction for desorption efficiency. 5.5 Determination of desorption efficiency. 5.5.1 Importance of determination. The desorption efficiency of a particular compound can vary from one laboratory to another and from one lot of chemical to another. Thus, it is necessary to determine, at least once, the percentage of the specific compound that is removed in the desorption process, provided the same batch of charcoal is used. 5.5.2 Procedure for determining desorption efficiency. The reference portion of the charcoal tube is removed. To the remaining portion, amounts representing 0.5x, 1x, and 2x and x represents target concentration, based on a 10L air sample are injected into several tubes at each level. Dilutions of benzene with carbon disulfide are made to allow injection of measurable quantities. These tubes are then allowed to equilibrate at least overnight. Following equilibration, they are analyzed following the same procedure as the samples. Desorption efficiency is determined by dividing the amount of benzene found by amount spiked on the tube. 6. Calibration and standards. A series of standards varying in concentration over the range of interest is prepared and analyzed under the same GC conditions that will be used on the samples. A calibration curve is prepared by plotting concentration, G/ml, versus peak area. 7. Calculations. Benzene air concentration can be calculated from the following equation. Mg/m3 equals 8b/c/d, where A equals G/ml benzene, obtained from the calibration curve, B equals desorption volume, 1 milliliter, C equals liters of air sampled, D equals desorption efficiency. The concentration in Mg/m3 can be converted to ppm at 25 degrees in 760 millimeters, with following equation. ppm equals Mg/m3, 24.46/78.11, where 24.46 equals molar volume of an ideal gas, 25 degrees Celsius in 760 millimeters, 78.11 equals molecular weight of benzene. 8. Backup data. 8.1 Detection limit air samples. The detection limit for the analytical procedure is 1.28 ing with a coefficient of variation of 0.023 at this level. This would be equivalent to an air concentration of 0.04 ppm for a 10L air sample. This amount provided a chromatographic peak that could be identifiable in the presence of possible interferences. The detection limit data were obtained by making 1L injections of a 1.283 G/ml standard. Injection table. 8.2 Pooled coefficient of variation air samples. The pooled coefficient of variation for the analytical procedure was determined by 1L replicate injections of analytical standards. The standards were 16.04, 32.08, and 64.16 G/ml, which are equivalent to 0.5, 1.0, and 2.0 ppm for a 10L air sample respectively. 8.3 Storage data, air samples. Samples were generated at 1.03 ppm benzene at 80% relative humidity, 22 degrees Celsius, and 643 millimeters. All samples were taken for 50 minutes at 0.2 liters per minute. 6 samples were analyzed immediately and the rest of the samples were divided into 2 groups by 15 samples each. One group was stored at refrigerated temperature of -25 degrees Celsius, and the other group was stored at ambient temperature, approximately 23 degrees Celsius. These samples were analyzed over a period of 15 days. The results are tabulated below. 8.4. Desorption data. Samples were prepared by injecting liquid benzene onto the section of charcoal tubes. Samples were prepared that would be equivalent to 0.5, 1.0, and 2.0 ppm for a 10L air sample. 8.5. Carbon disulfide. Carbon disulfide from a number of sources was analyzed for benzene contamination. The results are given in the following table. The benzene contaminant can be removed with the procedures given in section 4.1. 2. OSHA laboratory method No. 12 for bulk samples, analyte, benzene. Matrix, bulk samples. Procedure, bulk samples are analyzed directly by high-performance liquid CHR, chromatography, HPLC. Detection limits, 0.01% by volume. 1. Principle of the method. 1.1. An aliquot of the bulk sample to be analyzed is injected into a liquid chromatograph. 1.2. The peak area for benzene is determined and compared to areas obtained from standards. 2. Advantages and disadvantages of the method. 2.1. The analytical procedure is quick, sensitive, and reproducible. 2.2. Reanalysis of samples is possible. 2.3. Interferences can be circumvented by proper selection of HPLC parameters. 2.4. Samples must be free of any particulates that may clog the capillary tubing in the liquid chromatograph. This may require distilling the sample or clarifying with a clarification kit. 3. Apparatus. 3.1. Liquid chromatograph equipped with a UV detector. 3.2. HPLC column that will separate benzene from other components in the bulk sample being analyzed. The column used for validation studies was a Waters Ubondapack C18, 30 cm x 3.9 mm. 3.3. A clarification kit to remove any particulates in the bulk if necessary. 3.4. A microdistillation apparatus to distill any samples if necessary. 3.5. An electronic integrator or some other suitable method of measuring peak areas. 3.6. Microliter syringes, 10L syringe and other convenience sizes for making standards. 10L syringe for sample injections. 3.7. Volumetric flasks, 5 ml and other convenience sizes for preparing standards and making dilutions. 4. Reagents. 4.1. Benzene, reagent grade. 4.2. HPLC grade water, methyl alcohol, and isopropyl alcohol. 5. Collection and shipment of samples. 5.1. Samples should be transported in glass containers with Teflon-lined caps. 5.2. Samples should not be put in the same container used for air samples. 6. Analysis of samples. 6.1. Sample preparation. If necessary, the samples are distilled or clarified. Samples are analyzed undiluted. If the benzene concentration is out of the working range, suitable dilutions are made with isopropyl alcohol. 6.2. HPLC conditions. The typical operating conditions for the high-performance liquid chromatograph are: 1. Mobile phase, methyl alcohol/water, 50/50ths. 1. Analytical wavelength, 254 nanometers. 3. Injection size, 10L. 6.3. Measurement of peak area and calibration. Peak areas are measured by an integrator or other suitable means. The integrator is calibrated to report results % in benzene by volume. 7. Calculations. Since the integrator is programmed to report results in % benzene by volume in an undiluted sample, the following equation is used. % benzene by volume equals A times B, where A equals % by volume on report. B equals dilution factor. B equals 1 for undiluted sample. 8. Backup data. 8.1. Detection limit bulk samples. The detection limit for the analytical procedure for bulk samples is 0.88 G, with a coefficient of variation of 0.019 at this level. This amount provided a chromatographic peak that could be identifiable in the presence of possible interferences. The detection limit date were obtained by making 10 L injections of a 0.1% by volume standard. 8.2. Pooled coefficient of variation, bulk samples. The pooled coefficient of variation for analytical procedure was determined by 50 L replicate injections of analytical standards. The standards were 0.01, 0.02, 0.04, 0.10, 1.0, and 2% benzene by volume.